So to do the math, we consider two cases. First, for VGS less than the threshold voltage, we have very little drain current. We ignore that drain current in most of our classes when we're doing hand analysis. You actually do have a small leakage potential for a small leakage current, potentially large leakage current if you apply a drain to source voltage across the channel, but we'll tend to neglect that leakage current for hand calculations. When the drain to source voltage starts increasing, we get first a linear increase. First a linear increase in the drain current, and then as the resistance of the channel increases, as it pinches off, the resistance increases, and we get the current voltage characteristic bends over till it becomes almost horizontal. For most of our hand analysis, we'll assume that saturation region remains horizontal and just correct for it when it doesn't. Some of you may be wondering, oh, how come that doesn't look like it's horizontal? That doesn't look like it's a higher resistance. We got a higher current flow in there, but actually it is a higher resistance. Let me try to demonstrate that. So we can plot the slope of this line. So there's the current versus voltage, case B. And here's current versus voltage in case C. The resistance of these two lines, the resistance corresponding to B would be the reciprocal of the slope of this first line. The resistance corresponding to the channel resistance corresponding to case C would be the reciprocal of the slope of the second line. First line in case B, line B has a steeper slope, so it has a higher resistance. Sorry, steeper slope, so 1 over steeper is a smaller resistance than case C. 1 over a smaller slope is a higher resistance in case C than in case B. Okay, so let's do some math as we go from the linear to the saturation regions. Let's zoom in here on this picture, 3D picture of the transistor, ignoring for the moment the channel insulator and the gate electrode. We have the source on the left, the drain on the right, N-type source, N-type drain. The drain to source separation equals a length L. The transistor has a width W. Directions: X vertical, Y from source to drain, Z into the plane of the diagram. Electrons move from source to drain, so that's a electron current density J. Actually, electron flux density J, corresponding to a positive current flow from drain to source. To obtain current from current density, we obviously have to multiply by the channel cross-sectional area. Okay, so let's go back to basics here. To describe the current density in the channel, we know we rely on two types of current flow: drift and diffusion. In fact, the current flow equals the sum of the drift and the diffusion components. However, other than at the drain end of the channel when we get the pinch-off happening, the channel concentration N remains roughly constant along the whole channel. So this dN dy term really becomes negligible compared to the drift current term in the first order approximation. We're going to use this model and neglect this small diffusion current. Negligible, really. You can calculate it yourself if you want to figure it out, but it's tiny compared to the drift current. So we ignore the diffusion, focus on drift. We have J as Q, mu, N, E for drift current. We substitute for electric field E, the definition, minus dV dy, and then do some math. So we have current density. To obtain Current, from the current density, we integrate across the cross-sectional area. So with respect to the channel width, dz, with respect to the channel depth, dx, we integrate j. J is q mu n dv dy. If you do the integral with respect to the channel width, as long as we assume uniform current flow across the device width, then integral of dz equals the channel width w. If you don't like that assumption, then we can offer you further study in our graduate courses where we consider the non-uniform effects of the transistor width, specifically the fringing fields that start occurring around the edges. But let's neglect that for the moment. So then we have to integrate, as we integrate q mu n dv dy dx. Okay, a bunch of those things do not depend on the depth of the channel. This 0 to xd we're talking about, that's the channel depth, not to be confused with the depletion layer depth. So we pull everything out that doesn't depend on the channel depth, namely mu doesn't depend on it. The potential at that location in the channel doesn't depend on the depth of the channel. So we're integrating from 0 to x of d minus qn as a function of x and y dx. This integral, we just don't want to deal with this integral. So when you have an integral that's too complicated to deal with, you have a couple of options. Number one, you can actually figure it out and solve it. Or in this case, it's easier to punt. Just pretend you know the answer, because we do actually know the answer. The answer is the inversion charge Q as a function of position y from source to drain. We'll calculate that momentarily, but assume for the moment that we know the value of this inversion charge Q. So we give it a nice name, Q sub I, plug it in, and we have our expression for current, W mu dv dy times Q. Now some simple manipulations follow. We multiply both sides by dy. We end up on the left with I dy. On the right, we have W mu Q dv. We integrate both sides from source to drain. On the left, we integrate with respect to position from x equals 0 at the source to x equals L at the drain. We're integrating a constant I, right? The current is constant along the channel. So the integral of a constant 0 to L dy equals I times L. On the right-hand side, W and mu do not depend on the voltage. We're integrating on the right with respect to V. So we integrate from 0 to the drain voltage, VDS, QI dV. So we have, after dividing both sides by L, the drain current I equals minus W over L mu times the integral 0 to V of Q dV. Now, I should point out at this point, the W over L ratio that we see here becomes an extremely useful knob for a circuit designer to control, because a circuit designer can often control for each transistor the W to L ratio. And we see here the W to L ratio determines the drain current. So we will often include those. And by the way, when we're simulating circuits with SPICE, W and L form clear, important SPICE parameters that we want to use. Actually, we've encountered a couple of other SPICE parameters here and there, but let's push forward. Okay, how do we deal with this inversion charge Q sub I?